about the interpretable graphic models for online.
Thank you. Thank you for the opportunity for giving this talk. I'm very excited to talk about this subject, and please interrupt me with any questions you might have, as that's the only interesting part of the talk are the questions usually. So it will be good for everyone. So in this talk, I'll introduce a little bit of collider physics for those that are not familiar with it. And then I'll motivate why, when trying to study collider physics, we need to improve our modeling of all the relevant processes that are involved in the experiments. And then after motivating this need for better modeling, I'll detail one possible avenue. Here we'll hear a lot about different models. So I want to give one possible perspective, which is the use of probabilistic graphical models, or as they are sometimes called, Bayesian networks. And then I'll show one very detailed example. I hope you'll interrupt every step of the way. Let's see how it goes. In which we apply these Bayesian networks to four-top physics. I'll introduce why we need to deal with four-top and why is it so complicated to work in that final state. I'll also say what it means. And then I'll leave it in the backup slides, but you can ask me afterwards if you want. We also apply this to quark gluon taggers, which I think also gave some interesting results, and mostly at this stage, interesting lessons of what we want to be able to develop when applying these Bayesian networks to real final state collider physics. So let me give the customary talk about the customary slide about the standard model. The standard model of particle physics is currently our best understanding of some of the most fundamental aspects of nature. However, we know that it's a limited model. We have some experimental hints, we have some theoretical problems. So we need to be able to explore the standard model to try to measure it to more precision, and also to try to search for new degrees of freedom. And right now, it's a fair question to ask, what's the best way to explore the standard model? So one of the best avenues to explore the standard model is to run collider experiments. So this is a very rough diagram of what a collider experiment is like. Basically, we collide, in this case, two protons. It could be different things. We have something that happens in the middle, God knows what. And then we have information, hopefully, about the building bricks of nature. And here I point towards the use of theory and simulators in order to try to infer what we get from the experiments, to try to understand what these results tell us, but also to try to design better experiments and better channels to study and to probe the standard model. And here I say theory and simulators, because for me the use of simulators is a fundamental necessity that one should always keep in mind. We don't only refer to the standard model. I mean, we should not only talk about the Lagrange, but also about the way to get predictions from this Lagrangian to the experimental results. So far so good. How do we use these simulators, and how do we use this theory to try to measure the standard model processes? Well, first, usually what we do is we perform dedicated analysis with the specific topologies in mind. We usually have a background hypothesis, we have a signal hypothesis, and these dedicated searches rely on this choice of hypothesis and on a very good modeling of this hypothesis. We need to know what we're looking for, and we need to know it with a certain degree of precision. So what we do is we implement a simulation pipeline from where we start from the background and signal hypothesis, which can be hopefully codified in a Lagrangian with some couplings and some masses. We have some event generators that are able to give us the expected events at a given channel. So we design the collider experiments, we search for a given channel, and we know what we expect for a certain background and for a certain signal model. So I'm trying to be very general. Please interrupt me or please tell me to move along. But usually what we want to do is the opposite. Now we have the measured events at a given channel, and we want to translate these certain measured events to a meaningful statement about the parameters of interest of our hypothesis. That is, we have some we can go using these expected events from estimation to inference. And here in collider studies, I like to emphasize that we usually talk about frequentist methods to try to get these statements about the parameter of interest. That is, we have some log likelihood, we have a profile log likelihood analysis or some marginalization over nuisance parameters, and we try to get from the measured events to the parameters of interest. So if we put it all together, we can have roughly 3 types of statements. The one that we all want, which is to discard the background only hypothesis, which is, for instance, a discovery of a particle like the Higgs, where the background was the rest of the standard model and the signal was the Higgs. Usually what we have is the background plus signal hypothesis discarded. This is basically all the searches for new physics in certain regions of parameter space. And then we also have background plus signal measured, which is the parameter estimation. For instance, if we want to measure the coupling of the Higgs to a certain set of particles, our background is all the rest of the standard model processes, our signal is the Higgs, and we can measure to a certain degree of precision the coupling, the mass, whatever parameter we want. So putting it all together, we have background plus signal hypothesis, we have the measurements, and we can relate them through modeling and through frequentist inference techniques. This is usually a very rough statement of what is mostly done so far in, let's say, for instance, Atlas and CMS. This is an example to try to make it a bit more pedagogical, in the sense that we have, this is a very nice Higgs search performed by Atlas. And this is, when I upload the slides, you probably can access the link. They show this nice picture of the collider, of the incoming beams interacting, and you can produce hard objects, the big quarks, the Higgs and the W. The Higgs decays to 2 Bs, the W decays to a muon and a neutrino. We miss the neutrino, which is this, let's see, can you see my mouse here? Yeah. Which is this disappearing beam. We have the muon, which is capturing the muon chamber, and we have the two B jets, which are hard and collimated because they come from the decay of the Higgs, and we see them in the calorimeter. So this is very low level information. Usually what we do in the Fino community is we want this high level observables, which is, for instance, here the invariant mass of these two jets. Put it together, we have the expectation, which we got from these event generators. We have the expected distribution in this high level observable for all our background processes, for all our signal processes. We can detect if we are measuring first this signal, and should be able to measure, we can constrain all the parameters of interest, which in this case was the coupling of the Higgs to the big quark, and also the production cross-section of the Higgs in association with a vector boson, in this case, the W. So this is, for me, this is a beautiful picture, but that's beside the point. This is currently the most popular way of thinking about models. However, even if with colliders we have been able to test our predictions to an astounding precision, we may fear that we are getting near the end of the line of this type of method. Why? Because, well, besides the fact that the energy and the luminosity can be, there can be a hard cut given the experimental constraints, the money constraints, there is a systematic limitation because of the need for simulations. Because we need such a high precision in such a high statistic environment, the computational cost can be driven to the roof. And also, there is no guarantee that the modeling is appropriate at this level. There is no guarantee that if we pump up the Monte Carlo, we'll get the precision that we need to measure to model the background properly. That's usually the problem. So far, so good. So here's what machine learning can come to the rescue. Let me emphasize that when I mean machine learning in a very specific way, because machine learning has been around for decades at experimental searches, at the phenomenological community. It has been around for decades, usually to pump up the previous method. It is useful to define a better high-level set of observables, some multivariate analysis technique. But here I mean machine learning to try to alleviate the problem with the use of the simulation pipeline. So what I mean is the use of semi-supervised and unsupervised algorithms, which from the cards I see is a very interesting subject for everyone. The idea is that we could maybe ease the dependency on Monte Carlo, and one has to remember that this is not trivial, and this is probably something we have to be very careful about, because when we are using any type of algorithm, we are introducing some bias that we have to be able to control. So there's no such thing as a free lunch. So the idea, one could say it very roughly, like we start with some model hypothesis, some data representation choices, which don't really have to be exactly background and signal, but can be a bit more general. We expect the data to respect some set of symmetries. We want to deal with some set of observables. This will help us decide what kind of algorithm we can apply. And here I still include the Monte Carlo, because the Monte Carlo is useful. It's powerful. It really has a lot of physics involved. And it would be foolish to say, I only care about the unsupervised and semi-supervised algorithms, and I forget about the Monte Carlo. So we can incorporate the Monte Carlo. We have to decide how, and try to get from this an improved task, which can be anomaly detection, event generation, event compression, unfolding. There are a lot of possible tasks that can be helped with machine learning. Here, I want to talk about one possible task in particular, which is the use of surrogate models. A surrogate model is an emulator where we replace a given process with a certain function, which can be preferable because of some set of reasons. Which is, for instance, accessibility. That is, we don't have access to the two probability distribution. We don't know it, so we want to be able to have a function that approximates it to a very powerful degree. Speed, maybe we do have the probability density function, but it's very hard to sample from set probability distribution, or very hard to turn it back and infer from it. So maybe this surrogate model can help us. Or storage size, which is also a problem. Maybe we do have a good probability model. Maybe we can sample from it very easily, but if we want to store it, it's very complicated. So we want a surrogate model that really compresses it down to size, and we can start from it again to try to recover all the results. Let me emphasize that empirical models are already incorporated in the collider framework. When we have to do what we call hadronization, for instance, there's a lot of empirical modeling because non-perturbative physics is impossible to do. So there are already a lot of studies of the impact of using empirical models. This is the appearance of what we call systematic uncertainties, the appearance of unphysical behavior. So we know we have to be careful when dealing with surrogate models. So this is what I have in mind when I say a surrogate model for a collider study. We have the probability of data given theory, and we can split it up using some factorization theorems in the probability of data given the stable particles, and the probability of these stable particles given all the steps of the collider picture. And in this sense, what we can think of surrogate models to try to replace one block or all the blocks at the same time. There are a lot of work in the literature to do this. And I think it's a really interesting problem right now to try to decide the best way to build these surrogate models, which is a lot of effort of the community is already going into this. It's not, but I want to talk about one particular thing which incorporates something that is very common in other areas of high energy physics, which is the use of Bayesian techniques. Probably the use of emulators is very common also in Astro. So I don't want to claim that it's the first use ever, but in collider physics, because of the power of the simulators and the power of the frequentist methods, we have not needed so much of these emulators and of these Bayesian techniques. They are already there. There is the NNPDF, there is the Bayesian neural network, there is the conditional invertible neural networks that are able to build surrogate models. And the idea is that Bayesian inference allows for a better evaluation of all the uncertainties and for an improved unfolding, when I mean to go from the detected particles to the, let's say, theory particles, where we can have a higher control over the parameters of interest. Yes, thank you. Yeah, to go, for instance, basically there are to go from the stable particles to the shower partons, for instance, in the sense that we can, from the data to the stable particles. I mean, from the detector, let's say you have a detector simulation, you can then characterize your detector response to every particle that goes through it, and then you can hopefully invert it and go from the detector measured objects to the produced objects from all your pipeline of standard model physics, let's say.
So for instance, if you had a proton going to the top, you would take the final state and reconstruct the top.
Yes, if you have all the possible, yeah. Usually you cannot do it even if you can unfold because you are missing a lot of, for instance, the neutrinos. The missing ET is always a problem. So if maybe you can unfold and match some of the detected objects to the in some sense lower level objects, but it's not a guarantee that you can reconstruct everything in the final state. Yeah, that's a problem. But yeah, it's a very interesting point. Yeah. Thank you. So for me, intuitively, Bayesian always sounds good, but that's at least for me, because it really helps you control all the modeling assumptions and to really get a self-consistent way of going from measurements to parameters. And now the good thing is that it's becoming more possible. There are a lot of key developments. For me, one key development is the search of differentiable programming with easy accessible codes like JAX or Pyro or whatever. And also a lot of inference methods like the black box variational inference and the simulation-based inference, where the interactabilities that are usually associated with this Bayesian framework can be sidestepped to some degree, and it becomes feasible to incorporate it into some standard model analysis or some collider analysis. So for modeling in particular, there is a lot that we can take advantage of, and there is a lot of things already done. For instance, the use of GANs, VAEs, and the shower deconstruction algorithms, LDA, topic models in general, where we have a lot of surrogate models that are built at least with some Bayesian undercurrent. Always, and this is the thing that I really like about the use of graphical models, which really brings it to focus, is that we need to keep in mind that the modeling has the same requirements than event generators. We need to have models that are physically meaningful, that is, that we can understand, we can explain. And this is a bit harder to achieve than with the event generators, because we need to bake the physical bias into the model in a way that still allows for the model to work. The model has to be expressive enough, but also we have to be able to run inference on the model. And this inference should should be fast enough, should be small enough in the storage size, so it's still preferable to the use of simulators. So we need a Bayesian model that is both meaningful but also convenient. And this is the balance that you have to strike usually with these kind of methods. So let me talk now about one particular type of Bayesian models, which is the probabilistic graphical models or Bayesian networks. These are clear, interpretable, and testable, which is for me a key feature, way to state our modeling assumptions and to try to incorporate the physical bias into the model. There is a vast literature on this, on both implementations and inference, a lot of dedicated software, and also usually if you do it simple enough, the code is simple enough that you can do it by yourself. And there are already a lot of applications in collider physics. For instance, topic models, which is one particular kind, has been applied to quark gluon tagging at high PT for top searches, and also quark jet modifications for heavy ion collisions. I put here the archive links for anyone that wants to check them out. And the idea is that a probabilistic graphical model is an association between a graph and a joint distribution. The joint distribution is your model. The graph is a very intuitive way to express it, and also very helpful because it can lead you to some properties that can be hidden in the joint distribution. So we'll deal mainly with what we call the directed acyclical graph, in which the links between nodes, the nodes are, for instance, here X, Z, and Y, the links only have one direction, and there are no loops in which a single node fits into itself. That's why it's acyclical. So we have graph with connections that only go one way, and where there are no feedback loops for a single node, and we can get them associated with a joint distribution or a model. This is what we call a Bayesian network. As simple as this. What here I show is an example with 3 nodes, X, Y, and Z, and the joint distribution can be written in this very convenient manner in which X and Y are conditionally independent given Z. In this example, these 3 nodes are unobserved, but if I measure Z, this means that X and Y don't depend on each other. There are no causal relationship between these 2 variables. This is a bit more than I'll talk about here, but it's something I'm also interested in. But right now, what we care about is that from this graph, I can already tell that X and Y are conditionally independent given Z, and this is, as we'll show in 4 tops, this will be a really useful feature. So this is a probabilistic graphical model. There are 3 main advantages to start with for the use of graphical models. First is a very powerful visualization technique, which we should not take for granted, that it's able to express assumptions and can really help in designing and motivating models. Because if we can understand it in a generative way by looking at the probabilistic model and we can modify it accordingly, then we have a very easy model building technique. There's also a very economical representation of the joint distribution. We can express everything in terms of nodes, edges, and the different connections we have. And also it gives you insights into properties of the model. The model I showed before was very simple, but if you have a general graph, you can use, for instance, something that is called the D-separation criteria to try to search for all the conditional independence conditions, and that really helps you reduce the complexity of the joint distribution, because you don't need to express every single relationship between nodes. You can only express the ones that you need. Because here, I'll go back, here you need then to specify all 3 of these distributions, if you have some parametric way or a numerical way. And one very interesting thing is that inference can be expressed very efficiently in terms of the graphical manipulations. And you have some exact algorithms that in practice you don't use, but also some approximate algorithms that are really powerful and that can take full advantage of the use of this graphical structure. So this is something that I think it's really useful, and it's one tool that one has to keep in mind when trying to decide the use of models in a given task. Yeah. Yes. Yeah, you are assuming some independence, so you can go in certain blocks, and you can have these message passing algorithms that go back and forth. Yes, it's a bit similar to that. Yeah. No, you're very right. This idea of D-separation really helps you when you want to go forward and backward to do it in a very efficient manner, because you can go by blocks. Yeah, it's something that's very similar to neural networks in some sense, in that part at least. Yeah. So what I'm interested in right now is we can think of Bayesian networks for unsupervised or semi-supervised learning. In this case, we don't learn with labels. No, what we do is we want to model the generative process of the channel of interest of the data and try to infer the underlying appropriate classes and hopefully match them to some physical underlying processes, something that we do not observe directly, but which we know has to be tied to the observable data. This is non-guaranteed. We can have a model that really expresses the data very well, but which the underlying processes, if we think of it as a mixture of classes, do not reflect what we think of as the underlying classes. This is something that can happen, and one needs to develop some validation techniques to make this connection between learned classes and physical classes. We also can run a lot of statistical tests using the learning probability densities, either frequentist tests like using the likelihood, but especially Bayesian tests to qualify the learned data distribution, something like the evidence log ratio. You can use approximations like the EAC, the B criteria. You can use a lot of these tools built into the Bayesian model. What I'll also show is a very efficient way to test the assumptions of the model in the data to see if they match. This is the use of mutual, I'll use the mutual information to do that. And I can do that because I have a nice estimation of the probability distributions. So let's get to the problem at hand. I'll try to apply this tool that I have detailed to a given problem, which is the production of 4 top quarks at the LHC. This is based on a paper we did in collaboration with Ezequiel Álvarez, Barry Dillon, Dario Farughi, Jernej Kamenik, and Federico Lamagna. And the idea here is that we will select key observables and using some appropriate modeling assumption, this is, we'll introduce some physical bias, which will be, in this case, conditional independence. We will be able to disentangle 4 top quarks from the main background, which is TTW, and try and get from data the underlying distributions. It's not a done work in the sense that we show that the modeling assumption is imperfect and there is a clear way to better it, but it's a first step towards the use of surrogate models, in particular Bayesian networks, for learnable interpretable models with, and this is a key for me, verifiable assumptions. We can check whether our model was right in the assumption it took to try to reproduce the data density. So let me show why 4 tops is an interesting problem and why it's also a complicated problem. So it's what we call an increasingly sensitive standard model benchmark to be explored. There is a lot of experimental effort. There are a lot of impressive results in what we call the monolepton and the 2-lepton opposite sign channel and the 2-lepton same sign channel and multi-lepton. I'll focus on the last one and I'll show what it means to say 2-lepton same sign and multi-lepton. There is a great effort also to have state-of-the-art calculations and an improvement of the background modeling of the standard model prediction. And there is also, and this is very important for me at least, that 4 tops is one of the remaining well-motivated windows into a lot of proposed beyond the standard models, in the sense that measuring 4 tops with high precision can hopefully tell us more about the proposed degrees of freedom of physics beyond the standard model. Yeah, so let me discuss a little bit what's exactly 4 top production and why is it so complex. So we already have a very populated partonic final state in the sense that even if we restrict ourselves to the hardest process, the production of the 4 tops, we already have 4 final state particles, so the kinematic distributions are already non-trivial at this state, but still manageable, no? We have this production of 4 top quarks, in fact it's TT and TT bar, and 2 anti-tops. But the top is one of the particles that decays before reaching hadronization stage, so we never see the top, we only see the top decay products, even if we could reconstruct everything properly. And so we see how each top decays to a B quark, the blue jet in the picture I showed before, a W boson, and this W boson also decays into a lepton and some missing energy, some neutrinos. This is what we call the 2-lepton. Because I don't specify the charges, it could be same sign or opposite sign, but we have 2 leptons. And when we have 2 leptons, already the missing ET is complicated enough that we cannot recover the final state kinematic distribution exactly, which we can do for the monolepton or for the all-hadronic. But here already at this stage is already complicated. And then we needed to take into account things that we don't fully understand. We have impressive algorithms, but we need to incorporate the initial state radiation and the final state radiation. So we start to have jets that are radiated here in the initial state, some jets in the final state, which can really add multiplicity. So this is very hard to model, and also can make the kinematic reconstruction really challenging. So we will have like a jungle of particles in this final state. That's also why it's so interesting, because it's really messy. And here I'm not even discussing hadronization. So if we want to try to model this in the way that I was describing before, we have a lot of problems, because for 4 tops, the next to linear corrections to get higher precision are really large, and there is what we call the mixed corrections, which are comparable to the ones of pure QCD. So the bottom line is that here, theoretical calculations are both expensive and necessary. They are really hard to do, but we really cannot afford not to do them. So it's a huge problem. and there are a lot of accidental cancellations, and there is a clear dependence of the accidental cancellation, so it's hard to assess if we want to incorporate some proposed new degrees of freedom. It's hard to assess how these beyond the standard model degrees of freedom could change the cancellations, and so we could need these very expensive simulations for every proposed new signal model. So suppose we measure 4 tops to an astounding precision, so then, as always, what is a signal becomes a background, and then if we want to measure a beyond the standard model process, it's a new signal, but we cannot reuse all the previous calculations. We may need to do it all over again, and this is a huge problem. So let's talk specifically about the 2 leptons same sign, in which the 2 leptons have the same charge in the previous diagram, and the multi-leptons in which at least another top decays into another W decays into a lepton. Sorry. So this is a very interesting channel because you have a comparable signal and background yield and a more controlled kinematic distribution. The irreducible backgrounds are TTZ, TTH, and especially TTW plus heavy flavor, which are, again, as the same order of magnitude. We'll focus on TTW in particular. But the idea is that here we have less jets, so it's less complex. But we have the problem of the missing ET. So it's still very challenging. So right now, the best measurements of the production cross-section are given by both CMS and Atlas. CMS measures something along what we expect, which is 12 femtobars, while Atlas measures twice the central value. It reports is twice the expected the standard model cross-section. So it sees it's twice as many 4 top events as it should. One can interpret it a bit like that. However, it's still comparable and it's still compatible with the standard model prediction due to the uncertainties. And so right now we say that we are compatible with the standard model, but there is some modeling assumptions we need to do to try to get the backgrounds to behave like we want, mainly some normalization factors. And this introduces a lot of uncertainty. So we would like to reduce this uncertainty. So the first uncertainty that is really driving the cross-section uncertainty again up is the high multiplicity. Because we have so many particles, the modeling is very hard, and then we need to introduce a large systematic uncertainty. Also, we have some data-driven techniques that are implemented to get some backgrounds. And also, the TTW cross-section is slightly above what we expect, and this is consistent also with other searches. So there may be some modeling issues there. This is addressed with a normalizing factor in the sense that we say, well, we expected a background model to give certain yield, but we see that that from data, our model was wrong, and we should increase the yield from this background process. And this is consistent along other channels, is well justified, but introduces uncertainties. Also, a big problem here, and this really puts everything into perspective if you want to deal with this with a machine learning algorithm, is that we don't have a lot of events. We have roughly, for current luminosities, for run 2 luminosities, we have 300 events. So it's not a lot. So this is also something that one should take into account when trying to incorporate machine learning here. We are talking about machine learning for low statistics. Yeah, so let's try to see what we can do. Hopefully, what we could do is try to improve our knowledge of 4 tops, try to improve the knowledge of the irreducible backgrounds. So if we could pump up the simulation pipeline, that would be great. However, getting a high precision is really daunting. It's really costly, and there's no guarantee that we can do it right. So maybe an easy step, which is what I want to talk about, is to try to reduce the Monte Carlo dependency by learning directly from the signal region and using semi or unsupervised techniques to try to incorporate the Monte Carlo and improve on it in a data-driven way that is able to keep it all verifiable. So in this work, where we detail a proposal to do this, we will focus on the 2 leptons same sign with a positive charge, non-negative charge, and also we will neglect the multi-lepton, and we consider only 4 tops and TTW. TTZ and TTH can also be incorporated easily. It's not a problem. It's just to keep things to have roughly 1-on-1 events. And right now, I'll ask you to focus more on the technique than in the simulation data set, but we can discuss it later if you want. And so the idea is we want to incorporate our imperfect simulations of the known physical process as prior knowledge and try to use an update of our knowledge using the measured data. So we will deal exclusively in a Bayesian framework where we take the simulations as prior knowledge and the measurements as the data we will use to update our prior knowledge. So, as seen in a previous work by Ezequiel Álvarez, Darío Farughi, Ernest Kameny, Roberto, and Alejandro, there are two low-level observables, the number of B jets and the number of light jets, that is all the jets that are not B-tag, are the ones that drive the discriminatory power between four tops and its main background, TTW. And so we'll focus on those two observables and try to model those. We'll keep things simple. And we will use a probabilistic mixture model in which we have one class generating each measured event. And we will try to learn this assignment because we don't observe it. If we had, then we could do everything. We will try to learn this assignment and model it as a latent parameter C. See it? Yeah, so far so good. So now we get into the equations. I'll show the plate diagram later. So what we do is for each event, we measure the number of light jets, which we call Jn, and the number of B-tag jets, which we call Bn. And we want to model the joint distribution of these two observables as a mixture of two processes. Background, which will be TTW, hopefully, and signal, which will be four tops. And this is achieved, and this is nothing, it's just an explicit writing of the likelihood. We write the joint distribution as a mixture of two classes where each event is generated by a single class. So this is the probability of a given event belonging to a given class. And this is the probability of the self-measurement given that it belongs to cell class. Yes. Sorry again. Yeah, exactly. Yeah, let's say one is a TTW, one is background, two is signal. Hopefully, this will mean that one is TTW and two is for top. We are modeling like this. It's not a guarantee that we can match the underlying classes to the physical processes. Hopefully, what you have to model is this, the joint distribution for a given process. So if you know this already, you can use some known inference techniques to get this, which is how much events you have that are for four tops and how much events you have for a TTW. You have that, and you can translate this into a cross-section, and you're measuring it. But you need to have this. So this is where the main modeling takes place. This is just a binomial distribution, no? Because it's either it's a coin toss. Yeah. Yes.
Can you just remind me what the Jn and the Bn are?
No, perfect. Thank you for the question. Jn, let's go back into the diagram here. Sorry. Yeah, so this should be perfect. So here you have the top decays into a V, and then you have the production of other jets coming either for the W decay or for initial final state radiation. This, yeah, the number of these. This is a perfect world. In reality, this is what we know, but these things have to be tagged. So a B can be mistaken for a J, and a J can be mistaken for a B. Also the leptons, but that's not really, no, but there could be more complexity involved. Not. This is ideally what we would have. We will see that in real data, the fact that we do not have this is a problem, and we have to address it. So in some sense, it's nice because you realize that the assumptions you made were too simple, but we'll get to that eventually. So, yes. No, you assume you don't have new physics. Ideally, if you have a good enough model that you can trust, you can include the case with and without new physics and do some model selection techniques using, for instance, an evidence ratio and try to decide which hypothesis is preferred. Because there is the possibility that the new physics is absorbed into one of these classes or both. And hopefully, if your model is expressive enough, the fact that you try 2 classes, 3 classes, 4 classes makes a difference, and you can choose the model that best balance explainability and complexity. But yeah, here we are not including new physics, but hopefully we can. That's a better way to say it. We need to be able to be sure that the model is expressive enough to capture the difference between absorbing new physics and not separating in a single class, and be able to say that you prefer the second choice. Yeah. Yes. Yes. Yeah, hope. You mean how to incorporate systematics, you mean? Yeah. Yeah, hopefully when you say this problem of modeling the jet distribution of this heavy flavor, this should be captured in here, in this joint distribution. Or maybe I'm mistaken. So what you're saying is there are a lot of systematics with the heavy flavor and the gluon splitting, no? Yeah, hopefully because you are here focusing only on the final measured number of jets and number of bees, you will be able to capture this as the feature of the model, absorb it into the joint distribution, and only get the number of events from these fractions. So if these are hard enough, so you don't need to introduce the building of these distributions. You only need to measure the distributions. Yes. You mean it's less prone to systematic modeling, to systematic uncertainties because of the modeling of these distributions, no? Yeah, well, here it will be encoded in the prior dependence, no? You start with some prior in which you try to encode this modeling, and you can see by varying the prior, you can add it as a hyperparameter of the prior as well, and try to see how much you absorb this prior distribution, how sensitive you are to this prior. No, but it's a very interesting question. No? Maybe we can discuss it later a bit more. Yeah, because maybe I don't understand it. Yeah. So any other questions? Yeah. Yeah, that's all we are saying here. Here, there are no other modeling assumptions yet. That could be the case. Yeah, we don't know it yet. We have to run some inference. Yeah. No. Exactly. Right now, there's no other modeling, just to say there are underlying classes. Exactly. Yeah. Exactly. And this modeling could have some prior parameters, which we'll talk about it, and there is where we really introduce. Yeah. So again, the probability of an event originating from 4 tops is P of 10, hopefully 4 tops. Let's call it 0 and 1, 1, and this will be the ratio between signal and signal transbackground events, hopefully. And these are the 2 probability mass functions, because we are dealing with discrete variables, so it's probably a PMF, not a PDF, but we will ideally obtain them from simulations. Because we are dealing with integer variables, the most general distribution we can think of is a set of multinomials where you have a probability for the probability for a single process to produce a single bin of J and B. So this is what we model with a set of gamma, let's say, parameters, which is a matrix of dimension. If you take into account the 2 classes, 2 times the number of possible light jets you can measure, the number of possible bit you can measure, -1 because of normalization. So this is when you start in this model, you have for the probability mass functions, you have this amount of parameters. You need to introduce an additional parameter for the fraction. So right now you have this number of parameters and you could control it. However, there is a problem here. You don't know any of these parameters, you need to learn it. So usually what you could do is try to obtain the best parameters using either a max likelihood or some Bayesian approach, which is the thing we will do, in which we treat these parameters as random variables with some prior probability distribution, and we need to update them with the data as it is encoded in the likelihood. So we need to write Base Theorem, which is this beautiful expression in which we start. We want to get the posterior on these gamma parameters and the mixing fraction, given the likelihood of measuring the data given those parameters, and a prior distribution over it, and the evidence, which is the integral of these over all possible parameter configurations. So we have the Bayes theorem. We can write it explicitly in our model as the probability of a given gamma matrix and a given mixing fraction, given all the possible all the measurements of J and B. This is the likelihood that we wrote before using the explicit representation of pi for the P of T. And this is the prior distribution, and this is the evidence, which is nothing more than the joint distribution of the data, which is what we can measure at the end. So this is what we start from, with the modeling assumption that there are two classes and that we can describe the joint distribution with a multinomial for each class, which is a very general assumption in this case because it's a set of discrete variables. So it's really, at this point, the powerful assumption is that we only have two classes, and that's something we will need to relax if we want to implement it in a realistic analysis, but right now it's a workable assumption. However, if you try to run some inference here, you see that the model is over-parameterized. Because each distribution is a multinomial, each class can absorb all the data. And you cannot avoid it except if you bias it too much and then you turn it into a maximum likelihood fit. So if you want to have enough freedom to infer, you need to introduce additional modeling assumptions on this joint distribution per class. This is mostly because we have one measurement of J and B per class. So right now we don't have enough information to disentangle, so we assume that the number of light jets and the number of B jets are conditionally independent given the class. Yes. Yes, you have each class is a multinomial distribution now for J and B. So each class can in principle absorb the full joint distribution by itself. There's no reason why it can't. The only thing you can do is to bias the model using the prior, not to try to break the degeneracy between the classes. But if you bias it too much, you don't learn anything. Yeah, the problem is that it collapses. It's what we call mod collapse. It can really absorb the joint distribution of the data into one class, or split it in unphysical ways because of how it has too much flexibility. Yeah, perfect. Thanks for the question. Yeah, so we have to introduce we introduce this additional hypothesis, which is that for a given class, the number of light jets and the number of B jets are independent. So we can factorize the underlying distribution. So of course, this is not true. Yeah, because of B-tagging, because there's a cross. Yeah. Yes. No. What I'm saying is that for a given process, the probability of measuring a certain number of light jets and the probability of measuring a certain number of B jets are independent. Yeah. Yeah, the multinomial is the probability of measuring a certain, each bin of the multinomial is not, is the probability of measuring a certain number of light jets and a certain number of B jets. But that doesn't mean that measuring one jet it's not that you're repeating you're not repeating drawings of a sampling a jet. You have a lot of possible outcomes, which is 1 jet, 2 jets, 3 jets, 4 jets, 1B, 2B, 3B, 4B. No, it's a specific structure, but it's general enough so you can absorb mostly all discrete distributions. But yeah, we can discuss it. Yeah, maybe it's so okay. So this is the meat of the model, let's say, where we introduce the working assumption, which is this conditional independence. So we can parameterize the probability of measuring a given number of jets, nj or j, as we call it here, as a multinomial with a set of parameters alpha, and we can do the same for measuring a certain number of b jets b with a multinomial beta. So now we have, instead of a single matrix gamma, a lower dimensional set of 2 matrices alpha and beta, which, if we count the number of parameters, is lower than before. So we have introduced some bias, some physical bias that really helps to learn from the data. So yes. No, will not be true. No. No, it is important, and we'll see how the fact that it's not true can limit our model. It is important. We use it for working as let's say, as a first assumption, and in a future work, we'll try. There is a way to relate them using, for instance, the b-tagging. Yes, you can use other assumptions. Exactly. No, but that's exactly the point. Thank you for the question, because you write the graphical model. I'll write it a bit later. I'll do the diagram, and you introduce it, and you can start adding whatever you want. So let's say we start with this product of two multinomials, and this is not the same as saying that the two variables are independent. That's the important. The conditional independence is a much weaker assumption than total independence. We only say that they are independent if we know the class. If we don't know the class, that is, when the distribution that we observe, which is the number of light jets and the number of B jets, with no class assignment, these two are independent, but are dependent, sorry. And what we know is that this dependence comes from the fact that we are not able to observe the class. If we were able to say this event is for top, this event is TTW, then in our model, they should be independent. But because we are not able to do them, in the data that we observe, the two variables are dependent. So what we need to do is to learn the mixture from the arising correlation that appears between the light jets and the B jets, and this arise of correlation appears because of the unobserved classes. So all the correlations can be related to the mixing parameters. If we do it in a supervised way, this would be naive Bayes, but we are doing it in a probabilistic graphical model, unsupervised manner. So now the likelihood has. No, this is to say, yeah, sorry. Yes. So suppose you have the data, no? The data distribution. So you measure all your events and you count. You put each event in the bin of the light jets that it has and the B jets that it has. You divide by the total number of events that you have a multinomial distribution. Now you have the frequencies. No? How do you split this into two multinomial distributions if you only measure one of these draws per event? Yes. Because we want to infer, because we want to express this in terms of physical classes. We need to separate two classes from the data. Right now we can't. Every assignment that we can get is trivial because it can collapse into a single mode, or you can split it in a physical manner. There's no physical, let's say, there's no physical difference that could arise between the classes, because you cannot, you can always absorb it in this joint distribution. There is no inductive bias to work with. It has no handle. Yeah, it's Yeah. Yes.
Is there a fundamental why including the
we can first we count the parameters and we know we are way below. So we know that now the parameters are much less than the joint distribution parameters. So if you have dj times dv minus 1, this is the total number of parameters you could fit from the joint distribution. We have less than that. That's the first intuition. Then empirically you can check by, for instance, in your algorithm by repeating and seeing that you don't have any mode collapse or mode interchange. You can change by looking at the inference procedure whether you are really meaningful in what you're doing. You have to be meaningful but still be able to recover the joint distribution. So that's the game. Yeah. Thanks for the question. Yeah.
So for every type of class, you're saying that the number of jets and like jets are not correlated.
Are not correlated for a given class.
Yes, but you know that these numbers cannot be the same class.
Yeah, you know, and because exactly, you know that they cannot be the same. So you have different distributions for each class, and they are not and there is a clear assignment. So you have to match a certain jet distribution with a certain B jet distribution. Exactly. Is this a conditional independence and saying that all the correlation you observe between these variables is because of the class probability, the class assignment? Exactly. Yeah. Exactly. Yeah. Perfect. No, prego. So what we are doing now is we are writing the likelihood as a product of for each for a given measurement JV, you marginalize over all class assignments. So you have the probability of having a certain class, the probability of measuring jet J, number of jets J given class T, and the probability of measuring number of jets B given class T. So this is how we are writing the likelihood. And these are the three sets of parameters of interest: the mixing fractions, the jet matrix distribution, and the B jet matrix distribution. This implies a specific covariance matrix. So this is the physical bias we are baking into. You can write it in terms of the covariance matrix between the jets and the light jets and the B jets, which has a given distribution that you can see vanishes if we have only one class. So this is another way to express the physical bias we are baking into the model. Yeah. Okay. So now Bayes' theorem, instead of looking for a matrix of, instead of this amount of parameters, now we reduce it to this amount. So if you have, for instance, 6 and 4 bins, here is 30, 29, 58, 59 parameters, but now you have 6 plus 4, 10, minus 2, 8, 16, 17 parameters. So you have a lot of parameter reduction by this conditional independence assumption, because you go from one big multinomial to two small multinomials, which each have a normalization constraint. That's where this minus 2 comes from instead of a minus 1. You have 2 because you have two classes, and this comes from the mixing parameter that you have to learn. So now the Bayes theorem looks like the probability of measuring, of having a given alpha, a given beta, a given pi, given all the measurements that you made, and with a prior distribution that we still haven't specified over each set of parameters. So here you start to see some factorization properties that are useful for the inference procedure in the priors as well. We need to specify a priors for the pi's, a priors for the alphas, a priors for the betas. So to specify the priors, and this is another assumption that we make and that makes inference easier. This is not to bake physical bias, but just to make inference easier. We will parameterize our prior distributions using the conjugate prior of the multinomial, which is the Dirichlet distribution. So a Dirichlet distribution is a distribution that samples multinomials. And the nice thing about it is that multinomial times Dirichlet equals Dirichlet, which it will not be the case for our distribution because we have a mixture of multinomials. But if you have a single multinomial, then it's a closed form analytical inference. And when you incorporate this into a mixture of multinomials with a clear conditional independence structure, this block structure will really help the inference. So that's why we use Dirichlets. So we have a given set of parameters, which is the eta, and the distribution of, in this case, will be pi, alpha, or beta. Given this set of etas, can be parameterized like this, where b is a normalization function, and we want to map our prior knowledge to this set of eta hyperparameters. So the idea is that our prior knowledge will be the Monte Carlo distributions, will be our modeling of these joint distributions. We will promote it from the likelihood, we will move it to the prior. So what we will do is we will relate the expected values under the prior distribution to the Monte Carlo prediction. That is what we will do. We will have our priors be such that the expected value of the relevant parameters are the ones we obtain from the Monte Carlo simulators. Yeah. So this we can do using a certain parameterization where we say that each eta is a normalizing constant, which will encode the uncertainty we have on the Monte Carlo distributions and the Monte Carlo prediction. So this is the parameter value through the Monte Carlo simulations. And then we can look at the mean and variance using this parameterization, and we see that the expected value of pi is this is given by the Monte Carlo prediction, and the variance is controlled by this normalizing constant. And this is a specific form that the prior takes, and putting this all together, we have the graphical model, which we then can enhance to include everything that we want in a later stage, for instance, B-tagging or of a jet scale uncertainty, whatever we want, we can include it here, hopefully. Then we see how we start from a given set of hyperparameters, which are the etas, which are not in nodes, because these are fixed by us. We could promote them to some random variables and introduce some higher hyperparameters that control the Monte Carlo, but we are not doing that. And then from this, we sample this set of random variables, the pi's, the alphas, and the betas, which are random variables that are unobserved. From the pi's, we can sample the class assignment for each event, and given the class assignment and the alphas and betas, we sample the observed number of jets and the observed number of B jets. So this is the graphical model we are using here, where this box means that it is repeated for each event. So we have one sampling that goes before generating the events, and then for each event we have sampling of Z and sampling of the observed variables. So this is the probabilistic model, which is fairly simple. We have either Dirichlets or multinomials, and it's all very nice, but we need to be able to infer the unobserved parameters from the observed parameters. That's the key. If we couldn't do this, then this is not useful, no? So the idea is that we cannot do it in an analytical way because the evidence is intractable, basically. The appearance of a mixture really complicates things. So there is a vast literature on how to do inference on these probabilistic graphical models and for Bayesian problems in general. We could do expectation maximization with priors to find the maximum a posteriori. We could do variational inference for some approximate fast and analytical structure of the posterior distribution. But we could also do some Markov chain Monte Carlo, but now only to get the exact posterior in a numerical way. Because our model is so simple, everything is multinomial or Dirichlet at this stage. Right now, what we can do is we can write a Markov chain Monte Carlo in Python that is very fast, that is very easy to code, and we can and we don't need to resort to a dedicated software. But if we start to add some other hyperparameters to control the Monte Carlo or to add some B-tagging or whatever, we could still instead make use of this dedicated software, and it could still be very manageable to do it. We could use some more complex Monte Carlo techniques as well. So let's consider a simple benchmark. I'll detail later how we do the inference. We'll do a simple benchmark where we have 500 events and a fraction of 30% of those are 4 tops. This is roughly a higher luminosity that we have right now, is 800 inverse femtobarns. What we'll do is we'll take the Monte Carlo samples that we have generated as the true data, and we'll smear them with some function to try to have a different Monte Carlo, let's say a harder Monte Carlo, and use that as what we will use as Monte Carlo in a true analysis. Because we don't have access to true data, what we do have is some Monte Carlo samples. We'll call them true data, smear them, and use that smear sample as a Monte Carlo, as a prior. We will not use a prior for the signal fractions. We will assume no knowledge on them and try to see what happens. This is not the case in a real application. We know we have some knowledge of the signal fraction that we expect from Monte Carlo studies. So we could also introduce some physical bias there. We will not do it to see how it works. So these are the two-dimensional distributions for TTW and for tops. We see at this stage that there is some violation of conditional independence, which comes especially for 4 tops because of imperfect betagging, but we can check whether this is a problem for the model or not. We'll check it later. And here are the one-dimensional projections that we use. These are the true distributions in solid lines and the smear distributions in dashed lines. We do a big smearing of the number of light jets to try to reflect the fact that that's where the high uncertainty is focused on. We have a fairly good distribution for NV. So the prior is really good for the number of V jets, but really bad for the number of light jets. And let's try to see if with that we can really correct what we don't know about. Yeah. So what we do for inference is that we call what we call a Gibbs Sampler, which is probably one of the easiest Markov chain Monte Carlo algorithms. So what we do is we have from the Gibbs Sampler, we will obtain T independent samples of the posterior distribution, and we can compute any expected value given this posterior distribution simply by histogramming over the samples. That's the idea here. So we can plot the marginalized distributions, and we can get, and to do this, all we need to do is to get the conditional distributions of one variable with respect to the others, which in this case, because everything is multinomial and Dirichlet, is really easy to do. So in our model, we can use a very simple Gibbs sampler, and we can get a posterior, samples from the posterior in a very cheap way. So for each parameter, what we can have then is the one-dimensional diagram and the two-dimensional correlations with every other parameter. So for instance, here we see for the fraction, we started with a flat prior, and we get a non-flat prior that is centered around the true value of 30%. We start from a prior, we feed the data, we run a Gibbs sampler, and we get this distribution. And then we can have also the correlation between alpha and beta. So you see that in the prior, we were far away from it and also uncorrelated. And here there is some correlations between these two sets of parameters that are induced in the posterior. Now the posterior is not a Dirichlet distribution, it's not a mixture of Dirichlet's, it's a non-trivial distribution which we get from the Gibbs sampler. But we see how it's able to capture and to really narrow down to the true values in a much closer manner. So we can group everything together. We can get all the one-dimensional means and variances for each of these parameters. So this is a dimensionality reduction. It's not the full posterior. It's an approximation to try to see how well we are doing. So what we see is that if we start from a broad prior, we see here 5 columns. Here is the distribution of NJ for TTW, the distribution of NJ for top, the same for NB, and the prior distribution. Again, we start with a flat prior distribution, and we get a non-flat centered around the true value. It's still a very broad distribution. But we see how we start from very broad, very uncertain distributions, and we really get a reduction of the uncertainty, and also a reduction of the certainty that encompasses the true values. So we are really finding in this toy model, in the sense that we only have 2 processes, we are really finding the 2 classes that we want. We have a little bit more trouble here, for instance, in the NJ case for 4 top, and also but it's in the sense that it's not really a descending distribution. It's a bit weird, and this is a limitation of the model right now. So what we see from running this and other benchmarks, we also try different fractions. We also try different total number of events. We went to high luminosity to see how it works. What we see here in general is that there's a good convergence. We always have some uncertainty reduction. We find it easier to fix in the sense that because we have more bins, we have more information for NJ, and we have less, we have a harder time in some sense fixing NB in the sense of reducing the uncertainties, and also in reducing the uncertainties on the fraction, which we started from a flat distribution. This is mostly because NB is really unpopulated for the higher values, so we don't have a lot of information there, which is the values that really make a difference between the processes. So if we have high luminosity, this ceases to be a problem in some sense. And the limitations in the fraction are probably a reflection of the flat prior and the modeling. So if we have a good set of simulations and we can improve on this flat prior, then usually we can get a better estimation on this. Because the main problem usually in this experiment, this four-top searches, is the light jet distribution, which is really hard to model. This offers hope that we can incorporate the model, the probabilistic graphical models, to try to get a better light jet distribution in situ using these probabilistic models. However, we need to be able to evaluate our models. Right now, I only show you that they look good, but this is not an evaluation, no? We need to be able to say what we do. So what we do to verify that our model is really learning something is to get the log likelihood ratio of the correct parameters given the prior and posterior probabilities. But this is something we did for validation, but it's not something we can do in real data, because if we had the real parameters, we wouldn't need to do any of this, no? So what we can do is to use to take advantage of the Bayesian framework to try to get a model selection, to try to select whether we have a good model or not. We can compute the Hellinger distance between the learned data distribution and the true data distribution, the same with the KL divergence. This is something we did a lot for this quark and gluon tagger I mentioned in the second slide, in the sense that we were able to show that there was a correlation between the accuracy of the tagger and the Hellinger and KL divergence of the learned data distributions. And this correlation makes it clear that you can use the unsupervised metrics to select a good model in some cases. And a very important thing is that because here we have a generative model, we can perform some sanity checks and try to see whether our modeling assumptions are right and whether they sustain, let's say, high luminosity. And we can also interpret what is going on. So what we did to validate our model is to check the explicit assumption of conditional independence using the mutual information. So the mutual information of two variables is basically the KL divergence, that is this not distance because it's non-symmetric, but this relative entropy between the full joint distribution and the product of the two marginal distribution. So this is exactly, but not exactly, but this encodes our modeling assumption. If we look at the conditional independence, at the mutual information condition on the class, we see here that this measures exactly our modeling assumption. If this is 0, which we can only be for infinite data, this means that our modeling assumption is correct. But we can rule out whether it's the true mutual information is 0 or not. We can have the asymptotic distributions. And if we can rule out that this is 0, this means that our hypothesis, our modeling hypothesis was incorrect, and we need to verify our model. So let me say that again because it got a little confusing. Here we have the mutual information between the two variables. For our model, if we condition of a given class, this should be 0 because we assume they are independent. This means that this is different from 0, this is not, this is 0, and this is 0. If you are able to show that this is not the case, that means our model is wrong. So that's the thing we are going to verify, whether we can say our model is wrong or not. So what we do is we generate some a lot of pseudo experiments in which we estimate the full data distribution and the two marginalized distributions, and we see the value of the conditional independence. And from this, we can get the asymptotic, the distribution of the test statistic of this mutual information, and we can see how it behaves when the hypothesis is true and when it isn't, and whether we can tell apart the two distributions. So it's more of a frequentist analysis in that sense than a Bayesian analysis. So what we see here is that for current luminosities, we cannot rule out either possibility. That is, if you look at these distributions, the p-values are really tilted towards high values. So if the bulk of the distribution was here, that means we can rule out a given hypothesis. In this case, this column is the mutual information, and this is the conditional mutual information. In our model, this should be tilted towards 0 because the two variables are not independent. But if you condition on the assignments, this shouldn't be towards 0. So what we see here is that the two of them at current luminosities are not, we are not able to rule out that they are 0. However, if you look, we did it with the realistic B-tagging, also with imperfect B-tagging, and we see that perfect B-tagging gives a better picture in the sense that conditional mutual information is still still far from 0, but the full mutual information is not, but it doesn't change the picture. This seems to point out that for limited statistics, the fact that we are not including B-tagging does not impact the model, and the model still works. We cannot rule out the working statistics, the working assumptions, because of low statistics. However, if we increase the luminosity to the high luminosity LHC, we see that for perfect B-tagging, this is maybe a bit, for perfect B-tagging, we really can't rule out the mutual information equals 0 hypothesis, but we cannot rule out, this is what is bulked tilted towards here, the conditional mutual information equals 0 hypothesis. That means that the mutual information is non-zero, but the mutual information condition on the glass assignments is 0 for perfect B-tagging. For imperfect B-tagging, this is not true anymore because this imperfect B-tagging introduces correlations between the two jets because we have some cross-pollination between the beams, basically. And this really breaks and appears this peak in the low p-value rate. So this means that for increased statistics, we should at least incorporate the B-tagging, which is something we can do, and is something we can discuss later, how to incorporate B-tagging and other features into the graphical model. Yeah. Yeah. Maybe, yeah.
Just trying to repeat what you said with perfect B-tagging of the LHC, your conditional model is actually cannot be ruled out because why would it?
No, but this is the conditional model that we learn from data. So in all these cases, we have learned the, yeah. I mean, I thought your point was whether we, yeah. 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 Yeah, no, that's the idea. Yeah, for perfect B-tagging, we should be able to learn it from data. Yeah, we should increase our graphical model. I'm sorry, I'm gonna. No, but we introduce a node in between, which is this cross-pollinating B-tagging with some B-tagging efficiency and some Gaussian distribution on this B-tagging efficiency. The problem there is that we wouldn't be able to do the easy inference procedure. We have to do a more dedicated inference to get the posterior, because now we have some distribution that does not lend itself so easily to the Gibbs Sampler. Maybe I will have to work it out, but we could do it in principle, and the inference should be doable. We didn't do it, so until you do it, you don't know if it's doable or not, but it should be. But you can incorporate it because it's a modeling assumption that you can write in a graphical model. The same would be, for instance, if you wanted to, if you had some distribution on the high power parameters of the priors,
relative to the factorization scale of the simulation. You introduce the factorization scale with some distribution, which you need to take into account, and then you get the, but it's non-trivial, I agree. That is more non-trivial because you need to morph the distributions, basically, of the priors. Yeah. We can discuss it later. So, from what we get here is that for high statistics, we need to incorporate the B-tagging. So for me, this is great because in a realistic scenario, we know that B-tagging relates the two things, and we are able to explicitly verify that. We are not hiding it somewhere. Our model is clearly testable and is testable in a way that is interpretable. We know why it fails. So for me, that's a bonus. To be able to know when your model is wrong, for me, it's a good thing. But that's a very subjective view. Anyway, so for this model, from this work, what we are able to do is to model the data with a generative process. So we assume conditional independence as a modeling assumption that is explicitly verifiable, and we can show that this could improve into the Monte Carlo estimations by treating them as prior knowledge and updating them using the measurements. And we are able to correct the light jet distribution, at least the central values properly. It would be better to have a more physical distribution, but that's something that with the incorporation of B-tagging should be a bit better as well. So what could we do next? Well, we could first increase the expressivity of our model by including further physical effects such as B-tagging. And once we do that, when we can try to tune the Monte Carlo generators on signal regions to have an explicit realization of how this would work, to try to measure the signal cross-section with reduced systematics to see if that happens, test for new physics effects, and also to adapt to other channels. So what did we learn from this? The idea is that it's very interesting to see for me what happens when we try to include the Bayesian network literature, which is really vast, into all these interesting problems we have at collider physics. And machine learning can enhance statistical analysis. And the idea is to take full advantage of the Monte Carlo distributions that are generated and try to reduce the dependence of them and try to reduce the uncertainty on this analysis. And this is a very subjective comment in the sense that I tend to value simpler models where we can really test the assumptions and we can incorporate domain knowledge by explicit modeling of the joint distribution. The problem with this approach is that it's hard to generalize when you don't have such nice distributions as, for instance, multinomials. Now, here I was dealing with the discrete variables, which you can model as multinomials. If you are dealing with continuous variables, this could be a bit trickier. There is hopefully a lot of development in this area. For instance, the use of deep exponential families and black box variational inference could provide a trade-off between the simplicity and the power that you can of the variables you can capture using this type of modeling. So in conclusion, collider experiments right now are providing us with an incredible and increasing amount of measurements, and we need to take advantage of it, and we need to step up the simulation analysis techniques. And for me, at least, Bayesian modeling, Bayesian graphical models can provide clear modeling and fast inference and deserve to be at least one possible tool, a first tool to try to incorporate when it is convenient. And that's what I wanted to talk about today. Yes.
So you do this work to obtain a better Monte Carlo, an improved Monte Carlo in a way. And then you use the Monte Carlo with the standard value with the equalizer.
Ideally, what you could do is you can use these models, yes, to do what you said. Now you get you tune your Monte Carlo to get the one. You could do it. You could start from the Monte Carlo and use the posterior distributions that you have. You can work from that. That's a first step, and that's the easiest step. Or maybe you can do some feedback loop that really searches for a Monte Carlo that is mostly invariant to this update procedure, in the sense that it's the one that most captures the signal region. If you have the Monte Carlo that changes the then you know you have the one that's most adapted to this signal region, and then you can use the same settings of the Monte Carlo for a new physics generation, for instance. Exactly. This doesn't need to be the end of the analysis. It can provide an easily checkable first step to say, well, what happens to our Monte Carlo if we go through this process? Well, it's modified. Maybe I can use the posterior. Maybe I don't like the posterior because it has some unphysical features, but I can search for the Monte Carlo that really doesn't have these unphysical features, but also is the least changed by this iterative procedure. That's one possibility. But in the sense, it's a first step. No, it's not. Right now, we don't have incorporated detagging, so we have to do a lot more to show how it's if you're able to capture these features. But yeah. Thanks for the question.